Hello students, welcome to the class of complex analysis. In this video, we are going to discuss what is maximum modulus principle. So the statement of maximum modulus principle says that suppose we have a region G. Then we define an analytic function from G to C, complex plane C, analytic. Okay. And assume that there is a point A in G with the property that you consider f of a. F of a will be here. Okay. Then for any set, f z will be here. Okay. Then f of a and f z are complex numbers. Therefore, you consider its modulus value. Its modulus is a real number. So suppose this f of a, modulus of f of a is always greater than or equal to any f z, any mod f z. That means you consider a in G and you consider f of a here, f of a complex number. Then what is its modulus of f of a? It will be a real number. So modulus of f of a have the property that will be always greater corresponding to any set in G mod f z. Okay. Then we need to prove that this kind of function is a constant function. So when you have an analytic function with the property that mod f of a is greater than or equal to mod f of z for any set in this region, then that function is a constant function. Okay. So very important result for complex analysis, maximum modulus principle. So assume that G is a region and f is an analytic function. So f from G to C be analytic. Right. And also let A is an element in G such that mod f of a is greater than or equal to mod f z for every z in G. So we are going to prove that f is constant. Okay. Now, first of all, we are considering a neighborhood because A is an element in G. G is open. Since G is open, it is a region means it is an open set. Since G is open, there exists some r greater than 0 such that BAR, an open disk centered at A with radius r is contained in G. Okay. Now, so in this region, I first of all consider a neighborhood with radius capital R. Okay. Suppose this is our A is a center point and this is the radius capital R and this ball is BAR. Okay. Then also we choose one more radius small r. In this small r is strictly less than capital R. And then you consider the circle centered at A and radius small r. Okay. Now choose r such that 0 less than small r less than capital R and let gamma of t equal to, we define gamma of t and that gamma of t is this circle gamma of t, that is equal to a plus r e raised to it, the polar format of circle where 0 less than or equal to t less than or equal to 2 pi. Okay, and see this gamma of t is completely lies in BAR. Then gamma of t is a curve completely lies in BAR, the open disk BAR. Okay, so when we have a open disk and the function f is analytic in G. Okay, since f is analytic in BAR and inside that open disk we have a rectifiable curve gamma of t which is defined to be gamma of t equal to a plus r e raised to it where this r is the radius of that circle. Then fz has a representation. Fz can be written 1 by 2 pi I into integral over gamma fw divided by w minus z dw. This is we already proved in the first section. Power series representation of analytic function inside a open ball. So which is equal to 1 by 2 pi I into, when this is fz, what is f of a and what is w here, where w is a point in this region or w can be considered some gamma of t, elements in gamma of t, that is w is an element in trace of gamma. Okay, so 1 by 2 pi I into integral over gamma f of a, So that will be, instead of z we have to write a, w minus a dw. Z will be changed into a. So that thing equal to 1 by 2 pi I into integral. Okay. Now we replace this gamma equal w equal to gamma of t. And the replace w is equal to gamma of t means gamma of t is defined to be a plus r e raised to it. Therefore w will be a plus r e raised to it. Okay. And limit 0 less than or equal to t less than or equal to 2 pi. So this complex integral can be converted into, by formula, integral over gamma f d gamma f d gamma is equal to integral sum a to b f gamma of t gamma dash of t dt. So using this idea, f of gamma of t gamma dash of t dt. So using this idea, this can be written f of gamma of t gamma dash of t dt divided by this w is again replaced by gamma of t minus a. Limit is 0 to 2 pi because the limit of t is 0 from 0 to 2 pi. Okay. So that f of a can be written 1 by 2 pi I into integral 0 to 2 pi is there. F of a gamma of t. Gamma of t is defined to be a plus r e raised to it into gamma dash of t dt. What is gamma dash? This is gamma. Then what is its derivative? Derivative of a will be 0. Derivative of r e raised to it. That is r is a constant term. E raised to it. Derivative of e raised to it is e raised to it again. And derivative of it is I. Okay, this is gamma dash of t dt divided by, whole divided by, actually w minus a. And w is replaced by r e raised to it minus, sorry, a plus r e raised to it minus a. This is our w. Gamma is an element in gamma. So which is equal to, this a will be cancelled and this I will be cancelled. So you get 1 by 2 pi into integral 0 to 2 pi f of a plus r e raised to it. Again this r e raised to it, r e raised to it will be cancelled. So you get dt. So this is our f of a. Then what will be mod f of a? Mod f of a will be equal to 1 by 2 pi into modulus of integral 0 to 2 pi f of a plus r e raised to it dt. So this thing is less than or equal to 1 by 2 pi I integral 0 to 2 pi mod f of a plus r e raised to it dt. So which is equal to 1 by 2 pi into, what is integral 0 to 2 pi modulus of f of a plus r e raised to it. So this thing is always less than or equal to mod f of a. Okay, f of r e raised to it. So which means that this gamma or this w is lies in the trace of gamma. So when you varying these elements from trace of gamma, you find out f of that gamma of t and its modulus, then this thing will be always less than or equal to modulus of function value at the center point. So this thing is less than or equal to mod f of a. Okay, into dt. So this mod f of a can be taken outside. Okay, 1 by 2 pi is there. Okay, integral 0 to 2 pi dt, and integral 0 to 2 pi dt will be equal to 2 pi again. So which is equal to mod f of a 1 by 2 pi, and this thing will be integral dt is t from 0 to 2 pi. So this thing will be cancelled. You get mod f of a again. So now you get mod f of a is less than or equal to 1 by 2 pi into integral 0 to 2 pi modulus of f of a plus r e raised to it. This term, okay, is less than or equal to again mod f of a. Okay, actually which is equal to mod f of a, sorry, which is equal to mod f of a. So which implies 1 by 2 pi integral 0 to 2 pi, okay, integral 0 to 2 pi modulus of f of a dt will be equal to 1 by 2 pi I 1 by 2 pi integral 0 to 2 pi modulus of f of r a plus r e raised to I t dt. Okay. So actually these two values are equal. So here I done mod f of is a constant term. This can be taken outside. Then integral 0 to 2 pi dt will be 2 pi again. So this 2 pi will be cancelled. So this modulus of f of a can be rewritten as 1 by 2 pi integral 0 to 2 pi mod f of a dt. Because it can be taken outside, then you integrate t with respect to integrate dt from the limit 0 to 2 pi, it will be 2 pi again. So that the 2 pi will be cancelled. So this left side will become mod f of a itself. So which implies 1 by 2 pi integral 0 to 2 pi. All this term can be written here. So mod f of a dt minus 1 by 2 pi integral 0 to 2 pi mod f of a plus r e raised to I t dt is equal to 0. So that means can be write 1 by 2 pi integral 0 to 2 pi modulus of f of a minus f of a plus r e raised to I t dt is equal to 0. So which implies this 1 by 2 pi into integral values equal to 0 means this integral is equal to 0. 1 by 2 pi cannot be 0. So product of two terms is equal to 0. One is non-zero means other thing is equal to 0. So this integral will become 0. So we get modulus of f of a minus, actually this integral 0 to 2 pi mod f of a minus f of a plus r e raised to I t dt is equal to 0. Now integral mod f equal to 0 means that mod f is equal to 0. So f of a minus f of a plus r e raised to I t is equal to 0. So integral is 0. Riemann integral is equal to 0 means that integrand is equal to 0. Okay. So which implies modulus of f of a is equivalent to modulus of f of r e raised to I t. Okay, these two are equal for 0 less than or equal to t less than or equal to 2 pi. So when you consider gamma as a, what is this? This is our gamma of t. Okay. So when gamma of t is equal to a plus r e raised to I t, you get mod f of a is equivalent to mod of f of a plus r e raised to I t. Since this gamma is arbitrary, which will be true for any gamma. This is true for any gamma. Therefore, I can write modulus of fz will be equal to, instead of this gamma of t, I define z. This is true for any gamma and any number. Therefore, mod fz will be equal to mod f of a for every z in the region mod z minus a is less than capital R. And this gamma is arbitrary and the radius is arbitrary. Here this radius is also arbitrary. So what you get? Mod fz take the value only mod f of a. That is mod f in a value in this region. Mod f takes the value mod f of a. So which means that mod f, the function mod f is a constant function. It's a constant function on the region on the open ball mod z minus a is less than r, and that means this is bar. So in this open disk our function mod f is a constant function, but we want to prove that f is a constant function. Okay, so what is f? When f is a complex valued function, it can be written as some uz plus ivz, right? Then what will be mod fz? Mod f for mod fz will be u square plus v square, right? So since mod f is constant, mod f is equal to a constant means u square plus v square is equal to a constant, right? U square plus v square is equal to a constant. Okay. So I take u square plus v square is equal to some c, constant c. Then you differentiate this equation number 1, equation 1 with respect to x partially what you get? We get 2u ux plus the partial derivative of u with respect to x plus 2v vx is equal to 0. Derivative constant is equal to 0. So you get 2u ux plus 2v vx is equal to 0. Okay. Then you multiply this equation by the function v. When you multiplied by v, we get 2u ux plus, you multiply with by the function v. Okay, so 2u is there, v is multiplied ux plus 2v into v is v square, vx is equal to 0. Okay, then again we differentiate equation 1, this equation, with respect to y partially. So what you get? 2u uy plus 2v vy equal to 0. Now you multiply this equation by u. Multiplied by u. So we get 2u square uy plus 2uv vy equal to 0. This uy represent the partial derivative u with respect to y, and vy represent partial derivative of v with respect to y. Okay, so these are the new equations now, 2 and 3. Okay, now I am going to use the Cauchy-Riemann equation because the function f is an analytic function. So when function is analytic, I will write here, since f is analytic, it satisfies Cauchy-Riemann equation. CR equation, that is Cauchy-Riemann equations are held. What is Cauchy-Riemann equation? ux is equal to vy and uy equal to minus vx. Okay. So from equation 2, I am going to substitute ux as vy and vx as uy, minus uy. Okay. So what you get? You get again one equation. Now equation 3 can be written, 2u square is there, okay. Uy, instead of uy I can write minus vx, so this will be minus vx, okay, plus 2uv is there, 2uv, vy, instead of vy I can write ux equal to 0. So suppose this is equation number 4. So this 4 and 2, equation 2 and equation 4 have the common terms. This is vx, here it is vx, here it is ux and ux. So when you subtract these two equations, 4 and 2, equation 4 subtraction equation 2, you will get 4 minus 2 minus. Okay, these two terms will be cancelled for vx. So the rest of the terms will be minus 2u square vx minus 2v square vx equal to 0. Okay, so which implies minus 2vx can be taken outside, you get u square plus v square equal to 0. So this is the last equation we can have now. So minus 2ux u square plus v square equal to 0. So this is we have now. So you can see that minus 2 is not equal to 0 and u square plus v square is not equal to 0. Therefore ux is equal to 0. Ux is equal to 0. You get this. And when you arrange that equation by Cauchy-Riemann equation, then you subtract those two equation again, you will get uy equal to 0. When ux and uy are equal to 0, then this function u is constant, which implies u is a constant function. Similarly, we can prove that we can have v is a constant function. When u and v are constant, fz is equal to u plus iv is constant. So which implies our function fz is a constant function. Constant function. So we proved that our function fz is a constant function by using mod f is a constant function. Okay, thank you.